quiet voice or something. Okay, so today I want to dive into scheduling since we're running a tiny bit behind, and hopefully we can talk a bit about Deadlock, which is closely related. If you remember, scheduling, we sort of showed you this topology for tasks, which could either be threads or processes with single threads, whatever, that go through the CPU and then work their way through various queues when they exit the CPU. The simplest, of course, is the CPU is running a thread and timer interrupt goes on, the time slice expires, it gets put back on the ready queue, and this is kind of the process of a thread executing. And the question is really, how does the operating system decide when it's going to pull something off of the ready queue, which one to pull off? And surprisingly, yeah, you could do it in FIFO fashion, but that doesn't necessarily get you what you want. And so it's really this interesting question of what to do with the ready queue that leads to scheduling, and which is our topic for today. And essentially it's deciding which threads are given access to resources from moment to moment. And there I'm talking about the ready queue, but we could easily talk about any of the wait queues. We could talk about I/O queues here, waiting for a disk and so on. And so this idea of scheduling is pretty universal. And there are many goals, and we're going to talk about several of them today. So one of them could obviously be minimizing response time. If you've got a human sitting by the computer and they don't want to type a key and wait 5 seconds to see it appear on the screen, that would be minimizing response time. Now, it turns out that to minimize response time, you typically give up throughput because you're interrupting the processor a lot to try to respond to the user. And so a different thing, as I've mentioned, is maximizing throughput, which says I want to make the absolute most answers per second, or whatever my throughput measure is. And to do that, typically I don't switch very much because I don't want the overhead of switching, and I also want good cache state. And then somewhere in all of this is this weird notion of fairness. And the question of what is fair is things that people have written many papers about. And we'll see a few ideas of what fair is today. But hard to say what the right notion of fairness is. Now, we introduced this completely simple first come, first serve scheduling algorithm last time. And actually mentioned it the time before. And the idea here is you just have things on the queue, and you pull them off one at a time, and you run them to completion. Okay, and this is essentially what batch scheduling was like in the old original days of computing, when everything filled a room and was worth millions of dollars, and you wanted to make sure that you just ran everything to its maximum efficiency. And the reason I brought this back up is just because we're going to play off against this through the rest of the lecture. But if you notice, there are some parameters we can compute here. For instance, waiting time is the average waiting time is the time that each process ends up waiting, not executing. So if we have all three of these and they all arrive at the same time, process 1 gets to run first, so it doesn't wait at all. Process 2 waits 24 units, process 3 waits 27. Okay, and so if we add those up and divide by 3, we get an average waiting time of 17. We can also talk about average completion time. So process 1 takes 24 units of time until it's done. Process 2 takes 27 until it's done. So notice that this process 2 really only had 3 units of computation, but because it waited so long, it really took 27 total units to be done, and so on. And then we can compute that average. So are there any questions about this terminology? I don't want to dwell on it, but we good? All right, everybody good on that? So now let's talk about round robin. So the problem with the first come, first serve scheme is it's potentially very bad for short jobs. And we mentioned the standing and waiting to try to buy a single container of milk. There's a lot of milk that goes through this course, isn't there? So a single container of milk in the supermarket line, and the problem is if you get behind a really large job, you're in trouble. And so the round robin scheme is to try to break up the really large jobs in a way that, that's a robin, by the way. I'm supposed to break up very large jobs in a way that gives you a little more responsiveness in the face of really large jobs. Okay, that's pretty much the reason for it. And you basically have a quantum of time 100 milliseconds, 10 milliseconds, somewhere in that range. And when the quantum expires, you pull something off of the CPU that was running and put it back on the end of the ready queue. Okay, and you pull the next thing off the front and you run it for no more than 10 or 100 milliseconds, whatever your time is, and you keep doing this. And so we're going around and around, round robin, to schedule this. Okay? And if you have n processes in the ready queue, then each process in principle gets 1 over nth of the time. Why is that? Well, first one runs for 10 milliseconds, second one runs for 10 milliseconds. You just keep going through. And most of the time, n minus 1 time quanta, you're waiting on the ready queue, and then you get to run for your 1 time quanta, and then you wait for another n minus 1. And so that's why you end up with 1 over nth of the CPU time. And this Q parameter is really a tunable parameter. So we could set it to 10 or 20 or 30 or 100. Okay? And if Q gets infinitely large, we go back to first come, first serve, right? Because we wait for an infinite amount of time, probably we'll end up finishing whatever job, unless we're computing pi. If Q is really small, we end up with really tight interleaving, and really small, like every cycle you get into hyperthreading, if you guys remember what I talked about before. And however, if we don't have hardware support for multi-threading, then Q must be large enough that the context switch overhead doesn't dominate and you have 100% overhead. Okay? Does that make sense to everybody? Okay. Questions on that? This is the round robin schemes. I think you've talked about this in section, I'm assuming. No questions on round robin? Okay, pretty obvious, right? However, let's make sure we understand this. So suppose, for instance, we have 4 processes, and process 1 is going to run for 53 units of time, process 2 for 8, process 3 for 68, and process 4 for 24. And notice that we have a time quantum of 20. Okay? So if you were asked to hand simulate this on an exam, for instance, not that we would do that to you, maybe we would, you'd sit down and you maybe make something like this Gantt chart, which is basically just time ordering. And what you'd see here is that process 1 would run for, well, it's 53 milliseconds, let's say, long. And so we run for 20. And then what? Well, then our time quanta is up. So we put P1 at the end of the queue and we run P2. But P2 only runs for 8. Why? Why does P2 only run for 8? Yeah. That's right. It runs for 8 and then it's done. It doesn't need 20. So at that point, P2 is out of there. P3 picks up and runs for 20 because P3 is 68, right? P4 runs for 20 because P4 is 24. Then we got P1 gets to run again. And now notice that there is no P2 in here because P2 is done. And so then we run P3 for a little while, P4, and so on. Okay? Everybody on top of this sort of idea, right? And we can tune this time quanta. It could be 10, it could be 100, it could be 20. And now, of course, we can compute the waiting times, which are a little more interesting than they were with the first come, first serve examples. Because if you look at what process 1 is stuck with here, it waits. Here, process 1 is waiting while 2, 3, and 4 are running, and so we can compute that waiting time, that's 68 minus 20. And there's another period of time where P1's waiting, which is 112 minus 88. And you add that up and it's 72 total units of waiting. Okay? Nothing too magical there, yada, yada, yada. And when you now come out with the average waiting time, you see that the average waiting time here is 66 and a quarter. And the average completion time is 104 and a half. Okay? And, there we go. So the pros and cons of round robin is it's great for short jobs because notice we made P1 give up the processor so that P2 could run. If we hadn't had round robin and had first come, first serve, P2 wouldn't have actually gotten to run until after 53 units of time. But instead, P2 gets to run earlier. So the nice thing about round robin is even when you have a mix of long and short jobs, the short jobs still get a chance to run with a reasonable amount of time, even if they end up arriving a little late. Question, yes?
Is there a way of estimating if a job is shorter?
Is there a way of estimating whether a job is short or long? Yes, that's going to be a topic in, give me about 10 slides. But let's assume that if you could do that perfectly, you'd be great at the stock market, right? So you can imagine there's a little guessing involved here. Good question, though. Anybody else? Answer is yes, you can estimate. Okay. And since you brought it up, the really good point brought up here is how the heck do you even know what the runtime of P2 is until after it happens, right? How did you know that Google was going to go up today until after the day is over, and then it's like, oh, shoot, I should have bought it in the morning, right? Same problem here. So we have to come up with estimators when we start doing something here, and that's going to be a topic in a moment. So what about the round robin? So how do we choose the slice? Okay? And if it's too big, the time slice is too big, what happens? The response time suffers because the short jobs have to wait longer and longer before they're allowed to run. Okay? If it's infinite, we're back to FIFO, or FCFS, first come, first serve. If the time slice is too small, throughput suffers. Why is that?
Too much overhead.
Too much overhead, great. What type of overhead again? Context switching, namely moving the registers in and out. What else? Yes, caching. Okay, those are two pretty big overheads. Now, by the way, although the caching one problem doesn't go away, if you've got hardware support for switching every cycle, like a hyper-threaded scenario, the context switching overhead isn't there in the hardware. But you can only do 2 threads at a time, and so you're still going to have to do some swapping in and out of the processor to get all of your threads going. All right. So actual choices of time slice. So initially Unix time sliced at a second. Okay, think about that for a second. You're typing away, and every key, you got to wait multiple seconds before it's registered, because if there are 5 jobs running, you press a key, you got to wait 5 seconds for the key to show up on the screen. So that's probably not a great selection, right? In practice, you got to balance the short and the long jobs, and so typical time slices, just as a rule of thumb, you're at a party. You guys are becoming party animals because of my class. You're at a party. Somebody asks you, what's a time slice for a typical operating system? You can say, well, I know, somewhere between 10 and 100 milliseconds, and they'll just, they'll be amazed. Typical context switch overhead, somewhere in the 0.1 millisecond range. And so, roughly, if you got a 1% overhead due to context switching, you probably figure that's not too bad. If you get too much more than a percentage, you start getting to 5% and 10%. Now you're creeping up, and you start becoming more and more overhead and less computation. Okay? Now, let's take a look of a comparison between first come, first serve and round robin, assuming for a moment no context switch time, and the question might be, is round robin always better than first come, first serve? Might be a question. And here's a simple example. Suppose there are 10 jobs and each take 100 seconds of CPU time. The round robin scheduler would give it a quantum of 1 second just for the heck of it. All jobs start at the same time. What's the difference between round robin and first come, first serve? What was that? We have a play for no difference. Anybody want to come up? Okay, so how many people think there's no difference? Okay. You're going to argue for difference, or? Okay.
So the average waiting time will be longer because all of the jobs will basically finish near the end, whereas with FIFO, at least the first job would finish part of the end.
Great. So it depends on what your metric is. If your metric is average waiting time, in the case of round robin, everybody waits for a long time. In the case of first come, first serve, only some people have to wait a long time. Great. That's exactly right. So, you look here in the FIFO case, the jobs completed 100, 200, 1,000, whereas in the round robin case, they complete at 991, 992, 993. All right, good. So, round robin and first come, first serve finish at the same time, but the average response time is much worse under round robin. And, you got to imagine that if this is what you're doing, your cache state is getting toasted here because you're switching every second, and you could instead switch every 100 seconds. Okay, now second is Probably not a time at which caching is going to give you a lot of trouble, but if this is milliseconds, you very quickly start running into problems. Okay. Questions? Now, was there a question? Oh, I guess not. That was like this. So here is another example that here's our earlier example where we have P2, P4, P1, and P3. And the reason, why have I ordered them in this way? Yeah, shortest to longest. So P2 is 8 units of time and P3 is 68. And I've ordered them in a first come, first served queue order from shortest to longest. Okay? Now this, we know from last time, is the best average response time for this scenario because we do all the short ones first and then the longer ones and longer ones and longer ones, and we make the longest ones wait. And if you come up with average response time, that'll be great. And we can actually see this. So what we're going to put here is the best first come, first serve has an average wait time of 31.25 here, and an average completion time of 69.5, whereas the worst one, where we sort them in the other way, actually has an average wait time of 83.5, and the worst completion time is 121.75. So you can see the numbers are a lot worse if we pick the wrong order in first come, first serve. And this is exactly the, annoying thing at the supermarket where, Murphy's Law always makes sure you're behind the person with a cart full of things. Okay, that's just the way it goes. Now, somewhere in the middle here is probably going to be what happens if you do round robin. And it's kind of interesting. You can say, well, if the quantum is 8, if the quantum's 1 to 20 and so on, and you just sort of compute all these things. And by the way, I would never make you fill a table out like this during an exam. You'd be officially allowed to be annoyed if I did that. But notice that what's funny about this is the quantum that's best is not the smallest or the biggest, but somewhere in the middle. So what does that tell you? Well, that tells you that picking the perfect quanta is probably not something we're going to do on most systems. We'll probably pick one that's pretty good. Okay, but notice how, nonetheless, round robin is kind of between the worst and the best first come, first serve as far as these particular statistics are concerned, and that's a good thing. And that's why you very rarely see a system that's first come, first serve today, because the only reason for first come, first serve would be if there's no responsive need from that system, and the only thing you're doing is computing pi, for instance, right? Which is obviously important. Okay, so any questions on this? So notice, by the way, I wanted to show you these two particular columns. So here, this is an example where P2 is the shortest job, and notice how sensitive it is. It varies in its wait time from 0 to 145, and completion time from 8 to 153. So the short job is extremely sensitive to quantum and or ordering. The longest job, P3, really doesn't care, although, it's really happy here because it gets a 0, or here it's really happy because it's half. But by and large, the long job doesn't really care as much about scheduling as the short job, which really cares. And so that kind of says in this kind of responsiveness mode, your scheduling is a thing that's going to possibly mean a lot to your humans and not as much to your long jobs, perhaps. Okay. Now, that's a single round robin queue. Okay? Are there any questions on this, by the way? Just pretty clear? Now, we can have lots of queues if we wanted. In fact, maybe we make you do that as a suggestion for the current lab. But we could order these queues by what we would call priorities, and we could run each one of them round robin if we wanted. It's basically saying that, you run everything from the highest priority first, then the next priority, then the next priority, then the next priority. That's called priority scheduling, which you've been playing with already. And what's the execution plan here? Well, execute the highest priority runnable jobs to completion, and then you do the next one, then you do the next one, and each queue itself can be scheduled in any way you want, like with a round robin scheduler. Okay, so, we could have 3 jobs at priority 3 and some quanta pick at 20, and we can run them to completion, and then when there's nothing at priority 3, then we can move down to priority 2 and so on. Okay, that seems like a pretty simple thing to do. Problems with this strict priority scheduling is starvation is a pretty big one because the lowest priority jobs maybe don't get to run at all because of the high priority ones. And there's also this priority inversion problem, which you're busy addressing, which is essentially, it's not strictly an issue that priority scheduling is broken, but it's something that can happen in the presence of priority scheduling. And it basically says that, gee, there's some low priority task that holds a lock preventing a high priority task from running. And it's a low priority, it's a high priority thread is blocked on a low priority task that has a lock. That's the inverse of what I just said, but this means the same thing. And basically what usually, as we showed you in class a couple of times ago, this involves 3 threads for the typical scenario where there's a middle one that's running and a high priority one that's blocked and a low priority one that has the lock. But how do we fix these problems? Well, now we got to start talking about dynamic priorities. So maybe we adjust the jobs up and down somehow. We have heuristics involving some sort of interactivity or locking or burst behavior. This strict priority scheme can get very complicated very quickly. Okay, and you could imagine, just based on what I've told you so far, what do we want for the length of the jobs kind of at the high priority versus the low priority if we're optimizing for interactivity in humans? What would we like? Go ahead. Short jobs on top, long jobs on the bottom. Great. That would be a way to make sure that somehow our interactive folks are happy. Now the downside of that is really this starvation problem, which is if there's so many of these short bursts, maybe the low priority thing never runs at all. Okay. There's even an urban legend that they shut down the Multics machine at MIT one time, and there was a job in there that had been running for 10 years at low priority. Now, this is kind of an urban legend, but it gives you the idea there, okay? Now, so let's talk about so everybody on the same page about priority scheduling? Notice the priority scheduling is, the way to think about this is I've got a bunch of independent schedulers. Now, whether you actually implement this as one queue or a heap or whatever, that's another issue. But this is probably a good mental model. And this is, in fact, exactly what the 01 scheduler in Linux was a bunch of priority queues. We'll talk about that in a second. Okay. So what about scheduling fairness? So we haven't really talked about that. So strict fixed priority scheduling between queues is essentially unfair. And the fact that the long-running jobs that we say put at the bottom of the priority may never run. And so we must give the long-running jobs some CPU to make sure they're always making progress. And if you look, there's a trade-off between fairness and average response time. So as we make things more fair so that every job gets at least some CPU, we get less good average response time out of it. Our humans are a little less happy. Okay, so that's kind of a different way of looking at this trade-off here. We're trading off response time for fairness. Okay. Now, how do we implement fairness? Well, there's lots of ways. We could give every queue some fraction of the CPU instead of just saying run all of the high priority, then the next priority, then the next priority. So if you look at this, this is kind of like, express lanes in the supermarket. Sometimes the express lanes get too long and you get better service by going into the other lines. If you look here, what does that really mean? That means that we don't run priority 3 to completion, then 2, then 1, then 0, or if a new priority 3 comes around, we run it again. Basically what we do is we make sure that, say, 70% of the CPU goes to priority 3, then 20% to priority 2, then 10% to priority 1, and so on. And by making sure there's a guaranteed fraction that goes to the different priorities, we make sure that nobody gets stuck in the low queue forever without running. Is everybody with me on that? Now, of course, then you can start to say, well, wait a minute, once something's stuck in the low priority queue, maybe there are times when we want to bring it up. So a different way to do this is we could say, well, we got these priorities that are strict, but if something in priority 0 hasn't gotten CPU for a long time, we temporarily raise its priority so it gets some CPU time, and then we lower it again. Okay? Now, what I'm trying to do is not confuse you with too many options, but rather show you that there are too many options, and every one that you could think about, somebody has tried. Okay, that's why scheduling is a little bit of a black art. I'll give you the 01 scheduler, I think is a great example of that in a second. So, we can give each queue some fraction of the CPU, or we could increase the priority of jobs that don't get service. There are a lot of variants of Unix that have had ad hoc ways of saying, well, this job hasn't got enough service, raise its priority to an effective priority long enough to get enough service, and then lower it. And then what are the heuristics? Well, the heuristics are if it's been sleeping this fraction of time over the amount it's been computing, and you look up the phase of the moon, and there's something to do with, your horoscope for the day, then you decide to raise it by either 3 or 5 priority points. These heuristics are pretty crazy. Okay? And of course, once you commit to a heuristic, then every time you come out with a new version of the operating system, your customers previously have depended on the previous heuristic, so you can't afford to change anything because they get upset with you. Okay? So, yeah. But let's talk about lottery scheduling. This is one of my favorite simple ideas. It doesn't get used too much, but it's a way of thinking about a lot of things that are similar, which is basically every job gets some lottery tickets. Okay, so you imagine there's the space of lottery tickets, and every ticket is worth $1. And jobs that get a lot of lottery tickets get more CPU time than jobs that don't have a lot of lottery tickets. And how does this work? Well, in order to decide which job to run off of the ready queue, you throw a lottery and you randomly pick a lottery ticket, and the one who's got the lottery ticket wins and runs on the CPU. Okay? And, how do you assign tickets? Well, to approximate shortest runtime first, which I'm going to tell you about in a second, you can make sure that shortest running jobs get more than longer running jobs, and that's kind of a way of maybe getting some of this responsiveness. The way you avoid starvation is every job gets at least one ticket. Right? If every job has one ticket, then they at least get to run every now and then. Okay? So the advantage of this over strict priority scheduling is it behaves gracefully as the load changes. And adding or deleting a job basically affects all the jobs proportionately, because I add more jobs, I either add more tickets or I take tickets away from other people, but it's sort of a graceful degradation. Now, can anybody... Go ahead, question. Yes? So the idea, imagine a ticket's just a unique number from 1 to a million. And it's got a set of these numbers. And what happens is you throw the dice, you run a random number generator, it gives you a ticket number, and the guy who owns that ticket number gets to run. And then you do it again and again. You just draw a ticket. Now the way you make sure that every ticket gets used once is you use a pseudo-random number generator or something so that you really do work through every ticket. So there's lots of tricks there, but I don't know, did I answer your question? Yeah, so imagine that job number 1 has tickets 1, 12, and 13. And when you throw the dice, anytime that 1, 12, or 13 comes up, imagine a dice that has 13 on it, that's pretty cool, then you get to let that job run. Okay, otherwise, other jobs are going to run. Okay? So here's an example. So for instance, we could assume that short jobs get 10 tickets and long jobs get 1 ticket. This is a way to make sure we've got responsiveness. Then we can sort of say, well, if there's 1 short job and 1 long job, then the short job gets 91% of the CPU and the long job gets 9% and so on. So you can compute this, And basically all I've really said is I've decided that if I can figure out what a short job is, I give it 10. If I figure out what a long job is, I give it 1. And I get the short jobs get more CPU, and therefore things are more responsive. That's kind of a way of assigning. Okay. Now, of course, if there's too many short jobs, then we end up using all the CPU time, and there is no responsiveness anyway. And that's the essential problem with scheduling, which is you can never make up for the fact that you may have too many things to actually run on your CPU, and they basically all suffer. Okay, if you're in that scenario, then you buy more hardware. Okay, all right. So, any questions? Yeah. Yep. And then the lottery chooses like 10. Yep. Does the short job, does it lose, like after it does the CPU and then does whatever calculation instructions has to do, does it keep like 10? Or does Okay, good question. So the scenario, just to repeat for the folks in the cyberspace here, is if we have 1, 3, and 10 for a job, and we pick 10 and the job runs, does it give up 10? And the answer is in the short term, what happens is you assign these tickets and you just keep the tickets. And so every time 10 is drawn, that job gets to run. And so the ticket ratio between the different jobs is what gives you these fractions of CPU. There's something else which we really haven't addressed here, which is deciding whether you're a short job or a long job and handing the tickets out. So think of the ticket assignment as independent of the execution portion of this. So we've separated kind of policy from mechanism in this way, which is kind of one of the reasons this is a nice, clean way to think about things. That's a good question, though. Anybody else? Yeah.
When you run a new job, do you just issue more tickets, or do you take them away from the existing process?
The question is, when you start a new job, do you just issue new tickets, or do you take them away from others? Yes. Either of these are viable techniques. Some people who use things, we'll talk briefly about the CFS scheduler in Unix. They actually talk about an inflationary policy where you just keep adding tokens, essentially, versus, keeping a constant total number. Okay, good. All right, so exams coming up. I don't have a room yet for the exam. It's probably going to be multiple rooms because our class is pretty large. But for the moment, we're targeting Wednesday, March 11th. It's going to be essentially a 2-hour exam and a 3-hour slot. I forgot to mention this last time, except verbally, you get 1 page of handwritten notes, both sides, 8.5 by 11. We're not talking 22 by 41 sheets of paper. And there'll be no class on that day. And technically, all the material up to Monday previous, March 9th is fair game, although we'll tell you if that ends up being the case. Okay, any questions about the exam? Closed book. Bring your brain. Maybe bring a calculator. Yes.
Is that 3-hour time slot? Is that like 5 to?
My hope is that it's 5 to something. I don't know yet. It's getting a big classroom in Central Campus takes an amazingly long time, so I don't know. I'll let you know. That's my hope. After 5 somehow. So, okay. Checkpoint number 2 is due on Friday. Everybody's aware of this. You're well into the lab, hopefully. And we're getting pretty close to time for a survey. I'm sure you guys all wanted to tell me how much you love or dislike portions of the class, so we'll give you an opportunity. I'm going to be kind of curious as both the lecture format and how the sections are going and everything. So, all right, we'll probably do this with, I don't know, some Google Docs or some other format for surveys. Okay. Questions? Everything going pretty well? Groups are up to speed and you're kind of figuring it all out? So I did verify that anomaly we had for checkpoint number 1 of lab 1 won't happen again, which is your your design reviews will always be after the checkpoints are due. It just turned out that because of the way we moved that deadline, some rooms were already assigned and stuff. So, okay. All right, good. So how do you evaluate a scheduling algorithm? Before we go on, I wanted to say something about this. You build this algorithm that's got arbitrary complexity because you can. And the question is, how do you know whether it's a good algorithm? Well, one is you deterministically model it. You come up with a predetermined workload, you compute the performance of each algorithm, you compute how much CPU time it gets. This one doesn't happen too often. Okay, but you could imagine mathematically trying to model your algorithm. In fact, you could even go to queuing models. There are folks that actually do queuing theory analysis of algorithms, but you can imagine that heuristics and queuing theory do not mix very well. Okay, we'll probably talk a bit about queuing theory later in the term when we get into I/O, but suffice it to say that doesn't show up too often. What does that leave? What's left? How do you evaluate? What? Huh? Okay, but suppose I have a new algorithm. How do I know whether it's a good algorithm or a bad algorithm? Test it out, right? I was looking for something simpler than you're thinking. You test it out, right? You come up with some simulation or you actually build it, you run it on a real system, okay? And you got to come up with some actual metrics as to whether it's good or bad, like is it responsive or not, or what's the throughput? And then you measure it, maybe look for knees and curves or whatever, and that tells you whether it's good or bad. Okay, that's pretty much the approach, okay? And it's not a great approach when what you might be trying to do is evaluate correctness. The worst way to evaluate correctness is through simulation. Okay, but it may be the only way to evaluate something with a complicated heuristic, which you can kind of see the catch-22 that we come about in with scheduling. There was a question here first, yeah.
The difference between the first and the last is just the last one you actually build a system and the first one's a model?
Yeah. The first one's a model, the last one you build it, and typically the code you might come up with is too complicated to actually model. Now, maybe you can come up with some sort of event-driven thing that you feed with traces, and maybe that's somewhere between the two. So you're not actually implementing it in a real kernel, you're implementing it in an event-driven simulator and feeding traces to it. That's probably a little better than just implementing it and seeing whether it works, but it's hard to say. Yeah, there's a question here.
Aren't we trying to solve the halting problem here by trying to figure out, say, how long X program will run?
Well, there's several ways of looking at this, maybe as a halting problem or certainly an NP-complete mess, whatever it is. Sure. Hopefully with scheduling it's not halting because you're trying to actually run something, but no. Your point is good in general. I think these are just very complicated in general, and unless it's simply defined mathematically, it's very hard to do things other than some form of event-driven simulation. You're certainly not going to know whether it halts in the sense of what you're thinking. Okay, so let's be a little more sophisticated now. So remember, last time I briefly mentioned this idea of a CPU burst, and I wanted to emphasize it just for a second, which is if you were to look at the amount of time that a thread runs before it leaves the CPU, okay, which means goes back on some queue, you typically see something that's weighted a lot toward, and we're going to call that time a burst time because it's a burst of computation. It's typically weighted toward the low end of the spectrum. Okay, and however, there are things that are doing a lot of computation, indexing the web or something that take a lot of time. So there is a long tail, but there's this there's this large amount of short burst threads, and we talked about why that arose last time. Boy, I'm doing well today. And one of the reasons was typically interactive behavior like typing or whatever has very short burst time because you type a character, the character gets registered, it's put on the screen, and the thread is done, and it's going to wait for your next keystroke. Most I/O falls somewhere in that category as well because your CPU runs and then it does an I/O operation and it has to stop because it's got to wait for the disk to come back or whatever. And so these short little bursts tend to reflect a lot of I/O, whereas the long things tend to reflect a lot of CPU time. And, for obvious reasons. And so the question is, how do we exploit that to get some property out of the scheduler that we want? Okay? Now, so how do we handle a mix of different applications? Okay, so your cell phone, your laptop, whatever, there's no question that that's a mix of applications. And so maybe we can use this burst time to decide which application gets the CPU. And so we could consider some sort of mix of interactive and high throughput apps and ask how do we schedule them. Okay, now we've already sort of said something like the interactive ones get high priority and the high throughput ones get low priority, but we haven't really said how the heck do you decide where to put things, right? How do you decide whether it's an interactive app or not? And, do you trust an application to say, hi, I'm interactive, therefore I want priority? Does that seem like a good idea?
No.
Who says no? Why not?
Because then I could just write a program that lies.
That's right. You could easily write a program that lies, okay? Or worse, you might write a program that has a bug that accidentally says it's interactive when it isn't and messes you up because your interactive apps now are bad, right? So there's a couple of sides to this. And the other question is, should you have the same scheduler for servers, workstations, pads, cell phones? I mean, are the same schedulers going to be good across that whole range? Okay, probably not, because the ones on the smaller end are probably more about interactivity, and the ones at the high end are more about computation. Not always, but in general. Okay? Now, so assumptions are interestingly encoded. There's several that are encoded into many schedulers. And for instance, apps that sleep a lot and have short bursts must be interactive. Okay, that's an assumption that's built in. And things that compute a lot ought to get lower priority because they won't care and won't care about intermittent bursts from the interactive apps. So these are two assumptions that are built into a lot of schedulers. And they might or might not be true. Okay, I've certainly been implying that this is a good way to look at things, but they might or might not be true. And in particular, it's really hard to actually characterize apps because, for instance, what about apps that sleep for a really long time and then compute for a really long time? Are those interactive or computational? Or maybe they're doing I.O., who knows? Or what about apps that run under all circumstances, like they're real-time apps and they're monitoring drug delivery, and if they don't work properly, you die. Okay, well, that's something you probably want to actually run properly all the time. Okay? I would. Okay? So, or maybe, like your brakes. You want to make sure that when you press the pedal, the brakes actually come on. Okay, so we have a large number of different types of apps, and scheduling them is tricky. And so let's start with, what if we knew the future somehow? Could we always mirror the best first-come, first-served policy where what we do is we rearrange things so that it's always the shortest job first and then forward? Okay, because that looked like that had some nice properties earlier. Right? If we could figure out what the shortest job was first, then we'd run it first, and then we'd do the next one and the next one. And the problem, of course, is in the title of the slide. You got to know the future. Okay? And there is a policy that if you knew the future, you could run the shortest job first, which is really run whatever job has the least amount of computation to do. So you got a queue full of things, find the one with the least amount of computation. You're consulting the experts on the right, and you pick that one out, and you run it first, then you run the next one, and then you run the next one. Okay? And this is often called the shortest time to completion first. Okay? That's not a big difference. But there is a preemptive version of this, which says not only run the one that's got the shortest time left, but if somebody with a shorter time shows up, interrupt even the one that's running. It's a preemptive one. So we really run the shortest remaining time first. Okay? And this is really the difference between a preemptive and a non-preemptive policy. Question, yes?
Isn't this bad? Because say if I were malicious and I could just have hundreds and hundreds of jobs that I say are very short, just preempt it from everybody and just starve everybody.
So, you raise a good point, which is this not subject to manipulation? That's your question, right? And the answer is, of course it is, but let's not worry about that for the moment. It's a good question, though. In fact, it is a very good question, and we'll mention it in a moment. So these can be applied either to the whole program or to the current CPU burst of each program. And the idea is really get as many jobs out of the system as you can, and the big effect on the short jobs to get them out of the system right away, but a small effect on the long jobs. Remember those assumptions from earlier, and that's the motivation behind, let's say, SRTF. Okay? Everybody with me? Now, these are actually the best you can do at minimizing average response time if that's what you want. So they're optimal in that sense. And, since SRTF is at least as good as SJF, typically we just stick with SRTF, which is the preemptive one. So that's all I'm going to talk about for now. And comparison between SRTF and first come, first serve and round robin is pretty easy to think about. What if all the jobs are the same length? Well, SRTF becomes the same as first come, first serve. Why? If all the jobs are the same length, what happens is I pick one, it starts running, and now it's the shortest job, so it finishes first. And then I pick another one. It starts running, now it's the shortest job. And so SRTF becomes first come, first serve if all the jobs are exactly the same length. Everybody on the same page with that? Okay. And what if the jobs have varying lengths? Then SRTF and round robin to some extent make sure that short jobs are not stuck behind the long ones. Okay, so that sounds good. Kind of sounds like maybe SRTF has a nice property to it. Because remember, in this case, by the way, in a previous slide, if we happen to do round robin, we found that was going to give us way too much overhead over first come, first serve. But SRTF actually becomes first come, first serve in this case and becomes round robin-ish, better than round robin in the second case. And so it looks like it's better than both. Okay? Except for that minor problem that what? Got to look into the future. Okay? Now, here's an example, by the way, that I wanted to just make sure we're all on the same page here. So 3 jobs, A and B are both CPU bound. They're going to run for a week, so they're clearly not computing pi, something more pedantic. I/O bound for C, and it basically loops for 1 millisecond of CPU, then 9 milliseconds waiting for the disk. So A and B are the same long-running things. C is an I/O bound thing. It's like, a CD copy. You guys know what CDs are, right? They're these little round things that have digital music on them. I know you download all your music these days, but imagine a physical disk. So C is kind of like a disk copy or playing music, okay? And the question is, how do you schedule these? And if you only use one, if only one of them runs at a time, C essentially keeps the disk 90% busy. Which when we start talking about I/O, what you're going to realize is that keeping your I/O busy is really important because I/O is so much slower than the CPU. So maximizing I/O usage is actually an important goal. So C does it pretty well. It keeps the disk 90% busy. Okay, what about A and B? Well, they actually use 100% of the CPU. Now, if we use FIFO, what happens with this is once A or B gets in, it runs for a week. Okay, the disk is not well utilized, okay, because A runs for a week, B runs for a week, and then 2 weeks later, C runs. Okay? Now, with round robin and SRTF, it's kind of easier to see with a timeline. So here's an example of round robin with a 100 millisecond time slice. And what you see here is C runs for its 1 millisecond and then launches 9 milliseconds of I/O. And then we run A for 100 milliseconds, B for 100 milliseconds, and then C gets to run again. Okay? And I'm time slicing with 100 milliseconds, round robin. Okay? And notice that really means I'm interrupting A and B every 100 milliseconds, so I actually wait 200 milliseconds here before I run C again. And if you were to actually compute the disk utilization, I get 9 units of time on the disk every 201 units, which is about a 4.5% utilization. So round robin is not getting me anywhere close to my 90% utilization of the disk. Okay? Now, if I have a much faster time slice, 1 millisecond, then I would actually end up with something like this. C runs, and then I do A, B, A, B, A, B, A, B, A, B, A, B, then C, then A, B, A, B, A, B, A, B, and I get 90% of my disk utilized. But I'm waking up and putting to sleep A and B a lot, and so this is pretty wasteful. Okay? The final thing might be SRTF, where we really do get a 90% disk utilization. Why? Because C runs, it's clearly going to only run for a millisecond. It's the shortest job. It runs, it finishes, then A runs until the disk finishes and C's ready to run again. Then C runs again because it's the shortest job. So every time C shows up, it interrupts the thing running. SRTF, shortest remaining time first. And so C gets to go in every 10 milliseconds. It gets to run for a millisecond with this. And of course I'm running A. Why? Because the moment I start running A, it's now shorter than B. And so we won't run B for another week. Okay, are we good? Questions? So, except for this unfortunate thing about having to know the future, it looks like SRTF is pretty darn good, right? Yes?
No, it looks like it's pretty darn bad because you have to wait a week for B to run, right?
Well, if A and B, but they're doing computationally bound things, and so presumably, that's a good question, but we'll assume for a moment that A and B don't care about interactivity because they're planning to wait a week anyway, so the fact that they end up waiting an extra week probably doesn't matter. Now notice the funny assumption I've got in there, right? So there's a job that's going to run a week. Can it tell that it's delayed a while? Well, only if it's outputting some printing, outputting some values or something. So buried in what I'm saying here are my assumptions here that long-running jobs should run at low priority and not interfere with the interactive ones. We could talk about whether you buy that or not. Any other questions? Yes? Long-running jobs that require some interactivity, sure, you could come up with a few. I mean, certainly things that are outputting data on a regular basis but are going to run for a week. That's something where if they don't get scheduled, you would notice. Video games probably fit into that category. Although the thing about a video game is video games got a lot of I.O., so it's probably pretty bursty. So you got to think not the video games running continuously, but rather it's waiting for I.O. and doing something. Sure. Yeah, so what you're finding out here is that it's very hard to come up with a simple policy that meets all needs, right? That's great. I mean, I like what you're thinking here, right? Because you're sort of starting saying, well, wait, this is great, Professor Kuby, but what about? Imagine you're a company designing an operating system and you got to be able to play games, do interactive stuff, and compute pi, and you want to design a scheduler that's going to figure out what thing you got going and do the right thing for it, right? Okay, can you say heuristics? Tricky, right? It's a fun problem. Can you say job security as well? Because you create this really complicated thing nobody can understand, and then you're secure in your job, right? I'm not, by the way, saying that's a good thing. So SRTF has some downsides, right? Other than these sort of gaming downsides. One is it can lead to starvation. If there's too many small jobs, that was something you guys brought up, then basically the long ones never run because the short ones are always running, right? And it's somehow you got to predict the future, which seems like a pretty big downside. So some systems might actually ask the user, so are you going to run for a long time? They say no. Okay. All right. We've decided earlier that that's probably not a good thing. By the way, even non-malicious users have a hard time knowing how long something's going to run. How many of you have done what I would call experimental computer science, where you write some code, and then you're going to run it to see how long it takes, and you're totally surprised when it takes 5 days. Okay, you probably gave up on that and went and got a few cups of coffee. Yes, question. Oh, you're agreeing. Yes. So bottom line is you can never really know for sure how long a job will take, but in order to use SRTF, we would need that. Now, that doesn't make SRTF useful, because what's useful about SRTF is it's a nice yardstick for us to think about other things from, okay? And it is optimal in some way. Okay, so let's take a break and then come back, and I want to talk to you about ways of predicting the future. Don't want to miss this lecture. What was that? Yeah, isn't it great? Research department. The joys of clip art. I found it one years ago. Used it ever since. Yeah. Yep. We'll do that. It could be done today. Sure. All right. Sorry to rush you a little bit on your break, but I want to try to get through a couple of things today. So let's talk about predicting the next CPU burst. So we can approach this in the following way. We can observe history and assume that the application is going to behave similarly to the way it did in past, and base our predictions on that, okay? So notice right up front, I have to observe things before I can get any estimate of future behavior. And if you have an application that's truly random in its behavior, game over, okay? Because there's just basically no way to hope at predicting the future. So, for example, if we want to take SRTF but estimate burst length, we could have an estimator function, for instance, like this, which is, the estimated burst length is some function of the last burst lengths. And we could keep that in the queue, and then when we're ready to schedule, we look for the one that's shortest and we pull it out. Okay, and here's an estimator, by the way, that you've all used many times, but not necessarily thought it that way. It's a 2-element Kalman filter, which basically says I'm moving average of the last few items to sort of come up with an estimate. Okay, and the alpha factor kind of is sets how fast the previous history fades out. Okay, and that's a way, it's exponential averaging, of basically getting an estimate. All right? Now, this is something you've been thinking about, which is a multi-level feedback scheduler. And in this case, what happens is I have a series of queues, and I'm going to think of them in terms of priorities, but notice that I'm feeding from one queue to the next. And what this really means here is that each queue has a different scheduling policy. So this is round robin with a quantum of 8. This is round robin with a quantum of 16, and this is first come, first serve. And the idea is that I start running an item off of this queue, and if it expires its quantum, then I move it down to the next one. Otherwise, if it ends quicker than 8, I let it go. Okay, and so what does this do? I mean, what is the idea behind this type of queue? Say it again? Okay, remaining time first. Why? Good. So things that don't run very long stay toward the top, and things that run long eventually end up down at the bottom. And so what we're doing here is by feeding one queue into the next, we're kind of trying to estimate the burst time of this item by sort of moving its priority as it computes longer. And this was actually used in one of the very first operating systems, CTSS. And so basically you have multiple queues, each have a different priority, and each queue has its own scheduling algorithm, like round robins of different quantas, and maybe first come, first serve for the background. And lots of ways to deal with the quantum. So you can do exponentially increasing. You start 1 millisecond, 2 milliseconds, 4 milliseconds, 8 milliseconds, whatever. And we're basically adjusting the job's priority as follows. Details vary a lot, but for instance, the job starts at the highest priority. When the timeout expires, we drop a level and so on. And if the timeout doesn't expire, we push up a level or to the top. Okay. Now, long-running tasks get demoted. So this is kind of an SRTF approximation. Everybody kind of see that? I mean, how many people believe it's sort of an SRTF approximation? Why? Because things that are short tend to go to the top, things that are long go to the bottom, and just by looking at which queue they're in, we get an estimate of how long they're going to run the next time. Okay? And the scheduling is between the queues somehow. So we could have fixed priority scheduling where we always do the highest priority ones and then the next and so on. Or we could give time slices. Remember, we already discussed these as possibilities, where the highest queue gets 70%, 20 to the next, and so on. The first one kind of has a starvation problem. The second one at least reserves some time for everybody. Okay? And that brings up the discussion, which has come up several times today, is what about user actions that are foiling the intent of the OS designer? So the intent of the multi-level queue is to try to estimate the burst length. Right? I'm trying to do SRTF. What can a program designer do to give a countermeasure here? Yeah. Yep, lots of I.O. or sleeping. Yes. Try to shorten your burst length. This is amusingly, in the very early days of computer games, somebody figured this out, and actually they were playing Othello. Anybody here? How many people here have ever played Othello before? Kind of looks like small version of Go, but it's sort of fun with little black and white items on it. But anyway, the interesting thing about it was they figured out that by putting lots of printfs into the inner loop, they would do some stuff, printf, do some stuff, printf, and they ended up with a short burst length, thereby getting a higher priority, and they got more CPU time than their opponent, and they thereby did better. Okay? So any scheduler you come up with potentially has this really interesting countermeasure problem, which is what happens if the user knows enough about the scheduler to figure out how to do something with it. Okay? And boy, that gets hard. So let me tell you about the O1 scheduler. How many people have ever heard of the O1 scheduler? Anybody? So the O1 scheduler was a really big innovation in the 2.6.8.1 version of the Linux kernel, I believe. I'm maybe making that up in the last digit. But basically the idea was there were 140 priorities, 100 of which were real-time, quote-unquote, and the other 40 of which were user tasks. And this was a priority-based scheduler. So 40 of them, the ones in green, were user tasks, and you set their priority by nice. And 100 of them were real-time, where the priority was set inside the kernel. And notice that to the right is lower priority than to the left. So I decided, because I could confuse you this way, because I will, that in Unix, higher numbers are lower priority, because they can. Okay, so bigger nice numbers. Anybody here ever run nice? When you say nice plus something on a job, what that'll actually do is it'll raise the nice value and lower the priority. Okay? I thought I would sort of warp your mind a little bit. But why is this the O1 scheduler? Well, it was called O1 because no operation of scheduling took more than an estimate close to constant time. And the way they did 140 priorities is they had 140 queues okay, plus 140-bit mask, 140-bit mask that said which queue had something in it. So all the scheduler had to do was look at the bit mask, find the first one that was the highest priority, pull something off of the queue of that priority queue and run it. And it took zero time, or it took a constant time. And when they were done running a quanta, they'd recompute the next sort of quanta that was supposed to run, put it back on the queue, and everything took order one time. Wow, that was an innovation. It was a big deal over the ON scheduler that was there before, where every scheduling operation was proportional to the number of threads that were running. Okay? Now, there's two separate priority queues. There's an active and an expired queue. Now, by the way, I use the word queue here somewhat loosely because each queue had 140 queues, okay? So it was a queue of queues. And the idea was that things started in the active queue and on some priority, and when it expired, it went into the expired queue, and you ran everything in the active queue till they were all done, and then you swapped expired and active, and you were good to go. Now, before you get confused too much by that, this is just a way of keeping order one. Because what it says is, you run all of the top priority things, and when they're done, you put them on the expired queue, then the next priority, next priority, next priority, and when you're done, then you swap them, and it makes sure that every priority finally gets to run in every swap. Okay, so you can start seeing why you might do that. And the time slice, which is how much of the CPU you get, depended on priority, and so the higher priority or the lower number that you had, the more time slice you got. And so that's how you gave CPU priority. Okay. Now, of course, to make everybody happy, including the gamers in the third row here, we had to have a bunch of heuristics that were basically the user priority of a task was adjusted plus or minus 5 priority points based on some heuristics that tried to estimate how interactive it was. So things that were more interactive got a raise in their priority or a lowering in their priority number, and the things that were less interactive were moved down plus or minus 5 over its base priority. And there were heuristics for deciding when you did this, like for instance, you'd take the amount of, when a task sleeps for a long time, it gets a lot of interactive credit, which it spends when it's running, and there was some hysteresis in there, and there was something that if you had a task that was considered interactive, that it went back on the active queue instead of the expired. You guys catching all this? Back on the expired queue. And real-time tasks always preempted the non-real-time tasks, so there was no dynamic adjustment of priorities down there, but dynamic adjustment of the user threads. And wow. So now those heuristics became a really complicated part of the overall scheduler that, had to be tuned and somehow make everybody happy, and it just got really complicated. And I encourage you guys, there's a nice little paper out there on the 01 scheduler if you want to see how complicated it actually got. But eventually people were like, this can't possibly be good because nobody understands how it behaves. And so the completely fair scheduler first appeared in the 2.6.23 kernel was an alternative which was really going after not priorities in the classic sense, but sort of this different idea, which was imagine every job got a virtual CPU that had some speed to it. And all we really did was we adjusted the speeds of those virtual CPUs based on how we wanted it to behave overall, based on importance, and let the thing run from there. And so, for instance, it was basically inspired by network fair queuing. I don't know if anybody's taken 122. I think they talk about fair queuing in there, right? And so, basically, every process has their fair share of resources. It models an ideal multiprocessor where each process gets exactly 1 over nth of the processor, unless it's got a weight to it, because you want to give it more importance or less, and there was a way of weighting. Now, this is really not that complicated because everything's treated the same way. I haven't given you any heuristics right now. And basically, you have virtual time that, think of it this way, when one second of real time happens, if everybody's got the same priority, what actually happens is 1 over nth virtual time happens for everybody. Okay, because they each get 1 over nth virtual time. And so what we can do by making sure everybody moves forward at the same rate, that's basically the way this thing schedules. Okay, and all right. And I don't want to go into this too much longer, but I will point out that this particular view of making sure everybody has constant rate of CPU was much simpler and is actually the way things currently are. And I don't want to go into these details much more, but if you want to talk to me, this scheduler was a reaction to the complexities of the O1 scheduler. Okay, it's a much simpler way of doing things, and I'm not going to go into it in great detail, but well, what's faster and what's better? I would say the CFS scheduler was simpler, easier to understand, and overall gave indistinguishable or better behavior than the complex heuristics, and you knew why it behaved the way it does. So I would say maybe by that metric, CFS is better. Okay? Think of it as every thread, if I talk about this in an advanced class, I spend more time, but every thread is given a constant fraction of the CPU, and the scheduler is just making sure that they get their fraction. So it's like a big multiprocessor where each thread gets a fraction of the CPU. Okay? All right. So now I want to finish up with one last topic, which is real-time scheduling. So here, efficiency is very important, obviously. We've been talking about that, but predictability is really essential for real-time threads. And so in real time, performance guarantees are based around whether it's a task or class of a certain type. So you can imagine the breaks have a certain guaranteed behavior. Your video game has a certain guaranteed frame rate. There's guarantees are the way of looking at this. And real time is really about enforcing predictability, whereas everything we've been talking to up till now is about performance of some sort. Latency, throughput, not predictability. So there's a big difference between predictability and the other performance metrics you're used to, because if it takes a little longer for something to happen, but I know it will always happen in 10 milliseconds, you can do things you couldn't do otherwise, like run your brakes off of that CPU. Okay? Now, so hard real time, you've probably heard that term, is an attempt to meet deadlines for sure. So when I start this thread, it will run in no more than 10 milliseconds, period. That's a hard real-time task. And it basically, we say that nothing ever violates that. And there are many types of schedulers. EDF is earliest deadline first. LLF, least laxity first. RMS, there's a lot of these. And then there's soft real-time, which is a little squishier, soft. Okay? And basically what it says is we're going to attempt to meet the deadlines with a really high probability. But missing a deadline is not fatal. And so you can imagine, for instance, that looking at an MPEG stream is a good example of a soft, real-time requirement, because you want a basic frame rate, but you never know for sure how long it's going to take to decode each frame. And so I just want to make sure my frames are coming out at 30 frames a second, but each frame might not have an exact computation time associated with it. Okay? And so are there any questions on that? Okay, do you see how this is fundamentally different from everything we've been talking about? I mean, we're talking about guarantees and predictability, not about throughput. And notice, by the way, that hard real-time is in general very hard, because in order to make sure that I meet all the deadlines, what do I have to do? What's an essential requirement? Say it again? Certainly we have to go through all the threads, but how do we even know we can meet all the deadlines? Yes? You have to know the future, okay? Not quite as bad, but pretty close. What's something a little bit less bad than knowing the future? Similar.
Knowing how long something's going to take.
You guys are getting close. Knowing Worst case execution time. We don't have to know exactly how long any given execution is going to take. We just want to know what the worst case execution time is. And it turns out that there are ways with really simple code to try to estimate that. Okay? But it is a complicated analysis, because if I run too many threads and their worst case execution times sum up to more than 100% of the CPU, I'm not going to meet the deadlines. Okay? Soft real time, typically you just need to know an average. So these are much simpler than hard real time. So characteristics are typically that workloads are preemptible and independent. Times have deadlines D and known computation time C. And here's an example of 4 threads. The arrow up means when they arrive. The arrow down is when their deadline is. And so what we want to do is the real-time scheduling for this says make sure that all of these threads complete by their deadlines, because these deadlines represent the point in time where my real-time constraints have to be satisfied. They could be when the break better go on, right? Or they could be when that, that insulin or whatever it is has to be delivered, right? Those are the actual deadlines. Everybody with me on this? The gray boxes represent computation time, and that's a worst-case execution time for that particular thread. And so this looks like it ought to be a really simple scheduling problem. What's the problem? I mean, why should that not be easy? Okay? And so if you actually threw round robin at this, what you'd find very quickly is you just can't do it, because it's not based on the deadlines. You're just sort of multiplexing things. Okay? Here, you just died because your brakes didn't go off, right? That would be a bad way to end class. So there is something, I could go a long time into real-time schedules, but I wanted you to at least know about them, and there's more in your book. But earliest deadline first is a great example of a real-time scheduler that's very useful and pretty easy to understand. And tasks in this scenario are periodic, so they happen over and over again. So they have a period P and a worst-case computation time C, and it's preemptive, priority-based, and what it says is this is just like SRTF, except that what I'm saying is it's earliest deadline first. And so if you look here, suppose that these 3 tasks arrive for the first time at time 0. This guy has a period of 4, this has a period of 5, this has a period of 7, this one has a worst case time of 1, of 2, and so on. And if we start scheduling this, notice what I've got here. T1 will need to be done by this deadline, which is 1 period later, is typically the way you look at this. And so I'm going to run my 1 unit right away rather than running T2 or T3, because the earliest deadline is with T1. Okay? And then T2 now has the earliest deadline, so it gets to run. T3 has the earliest deadline at that point and gets to run. And why do I say that? Well, because at the time that this guy is satisfied, its next deadline is 4 later. And this guy's deadline is 5 later. Okay? And so all I'm really doing, if I schedule this, is I'm finding which one has the next earliest deadline, and I'm running that. And the cool thing about EDF is there's a very clear schedulability test, which is if I take C, which is the computation time, divided by period, and I sum all those up, as long as it's less than 1, it turns out you can do it with EDF. Okay, so the schedulability test is very simple. Assuming I'm willing to preempt. And notice back here, by the way, that there are scenarios where you actually would have to end up potentially preempting. Like here, this guy needs to run for 2, but he was started and ran the first unit, and then T2 now had an earlier deadline and ran. So these have to be preemptible tasks. Okay, how many people have ever heard of EDF before? Good. Not too many of you. So this is probably the gold standard of real time. It's very easy to think about. Okay? Questions? Now, we have a couple of minutes. I want to do one last thing. I want to get going on a topic we're going to spend much more time on next time, which is deadlock and resource contention. And resources now, we've been talking about CPU time, but there's many resources, not just CPU time, but also disk space and memory. There's at least 2 types of resources, those that you can take away and those that you can't. A good example of a preemptible resource that we've been talking about is what? CPU time. Okay? A good example of a non-preemptible resource might be anything you're protecting with a lock. The reason you put a lock there is because you can't preempt it or you'll get bad behavior. Okay? And resources may require exclusive access or be shareable, and we've certainly been talking about how write access to a database is a good example of an exclusive access thing. Read access to a database might be a shareable thing. And one of the major tasks of the operating system is to manage resources of all sorts. Now, we've been talking about CPU. We're going to move into memory next time. We're going to move into I/O soon after that. Those are more interesting resources maybe than CPU once you get past all the scheduling things. Okay? But that's what the operating system does, is it manages resources. Now, I wanted to get this question taken care of the difference between starvation and deadlock when we're talking about resources. And the difference is actually fairly simple. Okay? When we're talking about CPU, starvation says the thread waits indefinitely. So example is a low priority thread waiting for resources constantly in use by a high priority thread. Deadlock is an actual specific type of starvation that's a circular waiting for resources. Thread A owns resource 1 here. Thread A owns resource 1, so 1 depends on A, is waiting for resource 2. Thread B owns resource 2 and is waiting for resource 1. Do you see the cycle? That's the clear sign of a deadlock if you've got a cycle. Okay? So deadlock is a type of starvation, but not vice versa. Starvation can end, but doesn't have to, whereas deadlock can't end without external intervention. And what we're going to talk about next time is we're going to look at types of deadlock and conditions for deadlock. And that's a good example here is taking locks out of order in a way that gives you a cyclic dependency. All right? So, in conclusion, we've talked about a bunch of scheduling today. We talked about round-robin scheduling. We talked about shortest job first scheduling. We talked about types of multi-level feedback scheduling, which is really an attempt to estimate SRTF. Okay, we talked about lottery scheduling, which is an attempt to make sure that nobody starves from CPU time. We talked about the Linux CFS scheduler briefly, but it's basically a way of avoiding a lot of heuristics. And then we also started talking about real-time schedulers such as EDF. And so next time we're going to talk about resources and deadlock, and then we're going to move rapidly into virtual memory. I hope you guys have a great weekend. Don't forget checkpoint on Friday.